Karen Hunger Parshall, Commonwealth Professor of History and Mathematics at the University of Virginia, where she is currently chair of the Cochrane Department of History. She earned her PhD at the University of Chicago, where she wrote her dissertation on Joseph Wedderburn and the structure theory of algebra under the joint direction of Israel Herstein in mathematics and Alan G. Debus in history. She is especially well known for her work on the history of algebra, the American mathematical research community, and the internationalization of mathematics. In particular, she's published two highly respected books, volumes devoted to the British algebraist, namely James Joseph Sylvester, Life and Work in Letters, published by Oxford University Press in 1998, and James Joseph Sylvester, Jewish Mathematician in a Victorian World, Johns Hopkins University Press, 2006. Her most recent book, co-authored with Victor J. Katz, is Taming the Unknown, A History of Algebra from Antiquity to the Early 20th Century, and was published by Princeton University Press in 2014. She is the recipient of numerous awards, including a Guggenheim Fellowship. In 2012, she was an inaugural fellow of the American Mathematical Society, and just last year, she was awarded the Albert Leon Whiteman Memorial Prize, awarded once every 3 years by the AMS for outstanding contributions to the history of mathematics. This morning, she's going to be talking about the Roaring Twenties in American Mathematics, a subject excerpted from her forthcoming book, now under contract with Princeton University Press, The American Mathematical Research Community, 1920 to 1950, a new era in the development of our science. So without further delay, Karen Hunger Parshall and a preview of Mathematics in America in the Roaring Twenties.
Thank you, Joe. Is the microphone okay? Everybody can hear? Okay. So I want to take you back to December 1918. The University of Wisconsin's Edward Van Vleck was crazy to get back into real scientific work. The mathematician had just turned 54 months before the U.S. had entered World War I in 1917 and had engaged in the war effort as an instructor for the Student Army Training Corps on his home campus in Madison. With his usual 9 hours of teaching a week augmented by 2 additional 4-hour classes of freshman algebra targeted at the Army trainees, his war work, not surprisingly, had absorbed all of his spare time and energy. He had been completely diverted from the analytical research that he had been faithfully pursuing since his student days in Göttingen as a doctoral student of Felix Klein. The war had definitely marked a break in business as usual. In its aftermath, there was a sense within the scientific community more broadly, but within the mathematical community in particular, of entering into a new era in the development of our science. Every nerve should be strained to get our research back on its feet, in the words of Brown University's Roland Richardson. He was apparently not alone in his conviction. He and other American mathematicians poured themselves into their research in the 1920s. But what did that mean? What were their main research interests? Where were those interests fostered? What, in short, was the lay of the American mathematical research landscape in the Roaring Twenties? An answer to that question is what I'd like to explore with you this morning. Analysis situs, or what would today be called topology, was considered in the 1920s perhaps the most distinctive of the American mathematical research specialties. In fact, in surveying American mathematics in 1927, Göttingen's Richard Courant held that analysis situs was the one mathematical field in America which has perhaps had the greatest success. It came, however, in 2 flavors. Combinatorial, that is, algebraic topology, acknowledged by Courant, was fostered primarily at Princeton, initially under the leadership of Oswald Veblen. The other kind, point set topology, and ignored by Courant, was developed as an American specialty thanks to the efforts principally of R.L. Moore, first at Penn and then at the University of Texas, Austin. As students in the classes of E.H. Moore at the University of Chicago in the first decade of the 20th century, Veblen and R.L. Moore had both been influenced by the foundational postulate-theoretic agenda that the elder Moore had then embraced, and each initially attacked his own brand of topology in that spirit. By 1915, Veblen had given the 5th AMS Colloquium lectures on his evolving thoughts on topology. In particular, he aimed to present merely an introduction for his American audience to the problem of discovering the n-dimensional manifolds and characterizing them by means of invariance. In the published version of the lectures, which appeared only in 1922 due to his active involvement in World War I, Veblen took on the challenge of providing a more formal postulate-theoretic setup for algebraic topology. Veblen's work initiated a research focus on algebraic topology at Princeton that flourished beginning in the 1920s. Although his own interest shifted into the not unrelated area of differential geometry over the course of that decade, Veblen's student, and beginning in 1916 his colleague, James Alexander, as well as their colleague, Solomon Lefschetz, after his 1925 move from Kansas, continued to churn out new results in the rapidly evolving field. In 1926, for example, Lefschetz proved his famous fixed-point theorem, a result that provided an actual formula for counting the number of fixed points of a continuous transformation of manifolds. Veblen and Lefschetz also trained members of a next generation of algebraic topologists that included, in the decade of the 1920s, Veblen's student, Philip Franklin, at MIT, and Lefschetz's student, Paul Smith, of Columbia's Barnard College. By 1930, the time already seemed ripe for a new overview of results that Lefschetz provided on the occasion of his AMS Colloquium lectures at Brown. As he explained, while Poincaré had left the foundations of combinatorial analysis situs in, quote, a rather unstable equilibrium, it's largely to Veblen and Alexander that we owe the remedy for this state of affairs and the present improved situation. In fact, as Lefschetz saw it, a date marks the transition, 1922, when there appeared Veblen's excellent Cambridge Colloquium Lectures, Analysis Situs, which has deservedly become the standard work on the subject. In his own colloquium volume, entitled simply Topology, Lefschetz pushed beyond Veblen's work to deal with what he termed the new phases of the subject. Among those were the fixed-point theory that he had been developing, as well as new results on duality. In reviewing his former advisor's book, Paul Smith struck a nationalistic tone that reflected Courant's view of the strength of American algebraic topology. Analysis situs, he acknowledged, is a comparatively young science, but it's pleasant to reflect that much of what's been accomplished has been the work of American mathematicians, and to that work, the present volume is a distinguished contribution. The other branch of topology, point-set analysis situs, grew out of Georg Cantor's set-theoretic work and concerned topological spaces independent of any particular metric. It was this kind of analysis situs that ultimately attracted Veblen's slightly younger colleague, R.L. Moore. By 1916, from his position at Penn, Moore had published what proved to be a seminal paper on the foundations of plane analysis situs, and he had directed the thesis research of his first student, John Klein. In a sense, these two events defined the subsequent course not only of Moore's career as a researcher and teacher, but also what would come to be recognized as the Moore School of Point-Set Topology. Moore's 1916 paper harkened back philosophically and mathematically both to David Hilbert's 1899 Grundlagen der Geometrie and to Cantor's work in the 1870s and 1880s on the theory of point sets. In it, Moore took two notions, point and region, as primitive. If S is a class of elements called points, then for Moore, a region is a class of subclasses of points. That is, a region is a class of what Moore termed point sets. He then stated a number of axioms in terms of these primitives, and from them developed a topology of the Euclidean plane, giving topological characterizations of such notions as the simple arc and the closed curve. At the same time, he was careful to provide examples that demonstrated the independence of the axioms one from the others. This postulate-theoretic mode of reasoning, learned during his student days at Chicago, characterized much of Moore's subsequent research, as well as the eponymous style of teaching that he developed, in which students independently test conjectures and derive mathematical theorems from a set of axioms. Like Veblen before him, Moore used the occasion of his AMS colloquium lectures to codify his evolving ideas. Speaking at Boulder, Colorado in 1929, he laid out his point-set brand of analysis situs. When the printed volume appeared in 1932, 2 years after Lefschetz's account of algebraic topology, Moore had greatly extended the results derivable from the axiomatic setup for point-set topology that he had presented in his 1916 paper. Among them, the Moore-Klein theorem that gives necessary and sufficient conditions under which a closed set is a subset of an arc. As Harry Gaiman of the State University of New York in Buffalo saw it, this book will definitely be an excellent text from which to obtain an insight into the nature of the problems considered by the School of Mathematicians headed by Professor Moore. In addition to Moore, that school ultimately consisted in the 1920s of Moore students such as Klein at Penn, Raymond Wilder, first at Ohio State but then at Michigan, and Gordon Wyburn, ultimately at the University of Virginia. And students of these students, like Klein's students, Gaiman, Dudley Woodard, the second African-American to earn a U.S. PhD in mathematics, and Leo Zippin, first at Penn State but later at Queens College in New York. In the 1920s then, topology spread, especially in the Midwest and Northeast, as the United States sustained two largely distinct schools of topology. One was associated with Princeton and was actively spearheaded by Lefschetz after 1925. The other was headed by R.L. Moore, especially after he settled in Austin in 1920. Led by strong-minded advocates, these two topological camps fairly quickly found themselves in competition. An at times acrimonious rivalry between them continued unabated into the 1930s and served to spur the further development of both approaches. Now, Americans also pursued two types of geometry in the 1920s, differential and algebraic. But in this instance, there was no rivalry and little overlap between the respective practitioners. Of these two geometric research streams, differential geometry was unquestionably the more exciting and the more avant-garde in the 1920s, as leading mathematicians in Europe and the United States tried effectively to mathematize the general theory of relativity. However, differential geometry also came in different flavors. The more classical versions, which extended and developed late 19th century work, also had their representatives in the United States. For example, in 1906, while he was still at Berkeley, Ernest Wilczynski published the first American text on projective differential geometry, a sub-area that had grown out of work particularly by Gaston Darboux and Georges Alphand in France. After he assumed the professorship at the University of Chicago in 1910 that he would hold until ill health forced him to retire in 1923, Wilczynski not only actively pursued his own research in this area, but also produced almost 24 PhDs in it. Among them, Ernest Lane took over for his advisor in 1923 and continued to churn out graduate students. As Saunders McLean pejoratively characterized it, Chicago had become, in part, a PhD mill in mathematics in the 1920s. Moreover, what might be called its inheritance principle in hiring that is, the replacement of faculty members by their former students without particular regard for the evolution of newer and more exciting mathematics, resulted in a certain stagnation there in geometry, despite a prodigious output of new PhDs in the field. These doctorate holders, nevertheless, left Chicago to populate America's colleges and universities, desirous of better credentialed, more research-oriented faculties. At Columbia, Edward Kasner also worked in differential geometry along more classical lines. When 1919 brought the confirmation of Einstein's prediction that light rays bend when passing close to a large gravitational mass like the sun, Kasner directed his techniques to the problem of teasing out the more purely mathematical aspects of relativity theory, based as it is on regarding the space-time continuum as a four-dimensional Riemannian manifold. In particular, in a flurry of work presented to the AMS in 1921, Kasner studied the mathematical ramifications of Einstein's cosmological equations, finding, for example, that an Einstein space, that is, a special kind of four-dimensional Riemannian manifold, that wasn't itself Euclidean, couldn't be embedded in a five-dimensional Euclidean space. Like Kasner, Harvard's William Graustein also pursued differential geometry from a classical point of view, and in the 1920s drew on that background to treat questions arising from the mathematization of Einstein's theory. But it was at Princeton that Luther Eisenhardt bridged the old and the new differential geometry, and with Veblen inspired novel research directions. In 1923, for example, he published Transformations of Surfaces, in which he gave the first unified book-length treatment of the research that had been done up to that time on the generalization of three-dimensional differential geometry to n dimensions. Yet 3 years earlier, he had already begun embracing the new Einsteinian physics from a mathematical point of view. In October 1920, Eisenhardt had written to Einstein himself, inviting him to come to Princeton to lecture for a semester on his evolving ideas. Although that initial invitation was declined, Einstein did give a series of lectures at Princeton the following May. Their published English version became, in the words of historian Jim Ritter, the classic Einsteinian introduction to general relativity in the English-speaking world, and served as an implicit declaration by Princeton University of its claim to be the center of relativity research in America. Einstein and Veblen began to set up that center as early as the 1921-1922 academic year, when they offered their joint seminar on the theory of relativity and began to publish papers on their emergent ideas. In the first of these, joint work on Riemannian geometry and its generalizations, they laid the groundwork for what they termed the geometry of paths. As they explained, one of the simplest ways of generalizing Euclidean geometry is to start by assuming first that the space to be considered is an n-dimensional manifold in the sense of analysis situs. And second, that in this space there exists a system of curves called paths, which, like the straight lines in a Euclidean space, serve as a means of finding one's way about. One problem then became to determine under what conditions the geometry of paths is Riemannian. The exploration of that and other questions launched Eisenhardt and Veblen on a research agenda that occupied not only them throughout the 1920s and into the 1930s, but also new faculty members, Bob Robertson, John von Neumann, and Eugene Wigner, as well as a string of students and postdoctoral fellows, Tracy Thomas, Harry Levy, Morris Knabelman, Joseph Thomas, Aristotle Michael, Jesse Douglas, and Henry Whitehead, among others. Michael, in particular, engendered a so-called Pasadena School of Differential Geometry applied to physics at Caltech beginning in 1929. The 1920s also witnessed the continued development of algebraic geometry on American shores. But by the 1920s, much of that work was beginning to look dated in comparison with what was coming out of Germany, informed by the algebraic insights of Emmy Noether and others. Still, from their more shielded vantage point, America's algebraic geometers felt that the time was ripe to survey their field, and they did so in 1928 under the auspices of no less than the National Academy of Sciences. As the 1920s came to a close, they had no reason at all to doubt that their approach would have anything but a bright future. The survey's authors, Virgil Snyder, Arthur Coble, Arnold Emsch, Lefschetz, Francis Sharp, and Charles Sissom, reflected the changing demographics of American algebraic geometry. Virgil Snyder had returned from Göttingen to take up, in 1895, the teaching position at Cornell that he would hold for his entire career. There, he taught many in his classrooms, among whom was his future Cornell colleague, Francis Sharp, and trained in his style of geometric research almost 40 graduate students, one of whom was Colorado College's Charles Sissom. Coble had done his doctoral work at Hopkins under Frank Morley in 1902 and taught with his colleague Arnold Emsch at the University of Illinois for all but one of the years in the 1920s. Together, he and Emsch, like Snyder, produced like-minded graduate students throughout their long careers. Finally, Lefschetz earned his PhD at Clark University and, as I mentioned before, left Kansas for Princeton in 1925. Whereas in many regards his co-authors on the survey perpetuated algebraic geometry's past, Lefschetz reflected its future, with his dual interests in algebraic geometry and algebraic topology. Readers of the collaborative survey that these men wrote found lengthy lists of results and extensive bibliographies of mostly 19th century works, at least in the first 14 of the volume's 17 chapters. Those were the chapters written by Snyder, Coble, Emsch, Sharp, and Sissom. And those 19th century research agendas and techniques were what many Americans continued to employ in the 1920s. For example, Charlotte Angus Scott, an 1885 DSc from the University of London, who actually did her doctoral work under Arthur Cayley at Cambridge, moved to the U.S. to take a position on the first faculty at Bryn Mawr in 1885. Modeled on Hopkins, Bryn Mawr was the only women's college in the U.S. that offered graduate training, albeit in a limited number of subjects that were deemed key by the administration. One of those, though, was mathematics, and Scott crafted and animated a program in the field until her retirement in 1924. At the same time, she continued to pursue algebraic geometric research that focused on such classically 19th century matters as the intersections and singularities of plane algebraic curves. She shared her insights in the course of training 7 graduate students, 2 in the 1920s. One of these, Marguerite Lair, ultimately succeeded her on the Bryn Mawr faculty. An active community of American algebraic geometers in the 1920s shared Scott's perspective. Julian Coolidge at Harvard, Henry White at Vassar, Snyder at Cornell, Morley at Hopkins, Coble at Hopkins, and then Illinois. Their many students and others contributed to what Snyder described in 1932 as the simply appalling expansion of the field during the last half-century. He thus gave expression to an insider's view of an epoch in the history of algebraic geometry, much later characterized by Jean Dieudonné as that of development and chaos. At the same time that it contributed to the cacophony characteristic of the 1920s, Lefschetz's work also suggested some of the new research directions in the modern algebraic geometry of the 1920s. Dieudonné styled this new epoch one of new structures in algebraic geometry. In, for example, the influential 1924 monograph on analysis situs and algebraic geometry that he wrote just before leaving Kansas, Lefschetz applied the evolving techniques of algebraic topology to classical algebraic geometry, and thereby revealed the latter's essentially topological nature. Lefschetz thus foresaw a future for algebraic geometry in which new and very different techniques would supplant those of the past. The American geometrical scene of the 1920s, like its topological counterpart, was thus both subdivided and lively. Yet whereas the two topologies were in some sense young, the two geometries had much longer histories. Work from their 19th century classical periods continued to attract the attention and to define agendas of active 20th century researchers, especially in the Northeast and Midwest, but also in the West. As Harvard's George Birkhoff saw it in his 1938 assessment of 50 years of American mathematics, however, the areas of algebraic and classical differential geometry actually seemed most vital 50 years ago, and were more than somewhat spent by the 1920s. Still, in differential as well as in algebraic geometry, American mathematicians like Eisenhardt, Veblen, and Lefschetz were taking their fields in fresh, new directions and were being recognized for their efforts on the international stage. So even if it was in transition in the 1920s, algebraic geometry, at least in Oswald Veblen's view, had been the first wave of serious mathematical research to wash over the United States in the 1880s. A second, even more intense wave, in his opinion, finite group theory and its applications to algebraic equations, had originated in Europe and had also come ashore on this side of the Atlantic in the 1880s. By the 1920s, though, it was perceived that the field no longer occupied the whole horizon of American mathematical research as it once did. It had in particular been eclipsed by both topology and differential geometry. But be that as it may, it continued to represent a well-defined sphere of American algebraic research, thanks largely to George Miller and his efforts. In the 1920s, for example, Miller revisited the question of low-order simple groups. It had long been known that the alternating group on 7 letters is a simple group of order 2,520. Yet, in the search for all finite simple groups, it was natural to ask whether A7 was the only finite simple group of that order. In a letter to Cole, an extract of which appeared in the bulletin, Miller gave a proof by contradiction that indeed no other simple group of order 2,520 besides A7 could exist. Another natural big picture question was, what makes one group essentially different from another? Or in other words, what types of elements or internal structures do individual groups have that fundamentally differentiate them? Step by step, Miller approached this question too in the 1920s. Among others, he considered cases like groups generated by 2 operators of order 3 whose product is of order 3. Groups generated by operators of order 3 whose product is of order 6. And so on, and so on, and so on. He wrote a bazillion papers on these kinds of topics. By 1929, he had also determined all the abstract groups of order 72. Perhaps not surprisingly, these types of questions characterize the work of those who came under Miller's group theoretic sway. Algebraists like Miller's colleague at Illinois, Henry Brahana, Miller's students, Harry Bender and William Manning, and Manning's student at Stanford, Marie Weiss. The work of Weiss, Bender, Manning, Brahana, and others reflected the group theoretic program that Columbia's Frank Nelson Cole had introduced to the U.S. in the 1880s. As E.T. Bell saw it, though, that program seemed to have been pushed to the limit of human endeavor and even slightly beyond by the mid-1920s. Americans, nevertheless, continued to pursue research and to train graduate students in this vein through the 1920s and into the 1930s. But another American algebraic focal point in the 1920s, the theory of linear associative algebras, had been defined largely via the program at Chicago just after the turn of the 20th century, although hints of it had appeared as early as the 1870s and 1880s. In the 1920s, its main American proponents were Chicago's Leonard Dickson and Joseph Wedderburn at Princeton. In 1905, for example, Dickson had defined the notion of a cyclic algebra. That is, an algebra A defined by the relations xy equals y theta x and y to the n equals g, where theta of x is a polynomial in x which is rational in the base field f over which A is defined, and where g and f is not the norm of any rational polynomial in x. These algebras have dimension n squared over f, and for suitable choices of theta and g, Dickson had noted that they are division algebras. In 1914, Wedderburn had established a sufficient condition for a cyclic algebra to be a division algebra, and in 1920 extended his result to central division algebras, that is, division algebras with center equal to the base field. In particular, he showed that every central division algebra of dimension 9 is cyclic, and that Dickson's cyclic algebras are actually special cases of an even more general type of algebra, a so-called cross-product algebra. By the mid-1920s, Wedderburn had also had some success in extending the structure theory of algebras that he had developed in the first decade of the 20th century to infinite dimensional algebras, and had begun to work on what would ultimately be his 1934 AMS Colloquium volume, Lectures on Matrices. Now, Dickson was even more prolific. The late 19-teens and early 1920s found him hard at work on what was ultimately his 3-volume compilation of number theoretic results, The History of the Theory of Numbers. The insights he gained in doing this encyclopedic work, together with his algebraic research agenda, inspired 2 book-length forays in the 1920s, Algebras and Their Arithmetics in 1923, and the substantially extended Algebren und ihre Zahlentheorie in 1927. In these studies, Dickson considered linear associative algebras with identity over the field of rational numbers. His aim? To develop, for the first time, a general theory of the arithmetics of algebras, which furnishes a direct generalization of the classic theory of algebraic numbers, of such 19th century greats as Dirichlet, Kummer, and Dedekind. To that end, he exploited Wedderburn's structure theory, which, as Dickson recognized, implied that to study the arithmetic of an algebra A is to study the arithmetic of its semi-simple part. Dickson proceeded to show how to construct the integral elements and the units in A, as well as how to determine the properties of unique factorization from the analogous elements in its semi-simple part S. Indicative of his sense of the importance of this work, he lectured on it in 1924 in a venue no less auspicious, to him at least, than the International Congress of Mathematicians in Toronto. Dickson was also more prolific than Wedderburn in the production of new researchers who actively added to the store of knowledge about linear associative algebras in the 1920s. For example, Olive Hazlitt, one of his numerous women students, earned her Chicago PhD in 1915 for a classification of all, not necessarily associative, nilpotent algebras of dimension 4 or less over the complex numbers. From positions at Mount Holyoke beginning in 1918 and then at Illinois starting in 1925, she not only considered questions associated with division algebras, but also followed her advisor into the theory of the arithmetic of algebras. Perhaps Dickson's strongest student, though, was Adrian Albert. In his 1928 doctoral dissertation, Albert followed directly in the footsteps of both Wedderburn and Dickson in considering the classification of division algebras. He first pushed Wedderburn's immediately post-war results to the next dimension, showing that every central division algebra of dimension 16 over its base field, while not necessarily cyclic, is a cross-product algebra. This was the first of a flurry of papers in 1929 and 1930 in which Albert considered successively higher square dimensions in his quest for the general result. If group theory as practiced in the U.S. was more than somewhat old-fashioned in the 1920s, the theory of algebras was anything but. In fact, in George Birkhoff's assessment, there had been a great algebraic advance in the direction of a unified theory of linear associative algebras and their arithmetics in the U.S. in the immediately post-war years. That advance was due in no small part to the work of Wedderburn and Dickson, as well as of Dickson's students, especially Albert. These mathematicians actively engaged in a research agenda that also attracted the attention of some of the best algebraists on the other side of the Atlantic, and that would, in the 1930s, bring American mathematicians even more fully into competition internationally. Americans also pursued at least one other major research area in mathematics in the 1920s, analysis. And as with other areas, the principal loci of activity were widely agreed upon and recognized. At Harvard, William Osgood, Maxime Boucher, and their followers, like George Birkhoff, had, in Veblen's view, created a function-theoretic current that is one of the most important elements in the mathematical stream. While at Chicago, work on the calculus of variations was initiated by Bolza and continued by Bliss. So let's consider Harvard first. There, Birkhoff was actively pursuing a wide range of analytic topics, as well as training graduate students across the field. One of his areas of interest stemmed from the doctoral work that he had written under E.H. Moore at Chicago, inspired by work of his Harvard professor, Boucher, on asymptotic expansions of ordinary linear differential equations, boundary value problems, and Sturm-Liouville theory. In the fall of 1920, he was lecturing on precisely these topics, and in 1922, his 1922 PhD student, Rudolf Langer, was in the audience. Langer published 2 papers in 1923 that constituted his dissertation and that drew on results that Birkhoff had presented in his own doctoral work. One considered a class of differential equations different from that initially studied by Birkhoff and explored the expansion problem associated with it. The other, which was joint with Birkhoff, aimed to lay a matrix-theoretic foundation for the theory of boundary value problems of ODEs as a whole. At essentially the same time that Birkhoff and Langer were producing their very computational results, Birkhoff was also engaged in functional analytic research of a more abstract nature with his recently acquired colleague at Harvard, Oliver Kellogg. Their paper, Invariant Points in Function Space, laid out a general program of functional analysis concerning existence theorems that was arguably more effective than the obvious treatment by direct abstraction that E.H. Moore, for example, had advocated earlier. That's their assessment of what they were doing. In particular, they established the existence of 2 things. First, invariant points in a region of n-space convex toward an interior point under a continuous one-value transformation which carries points of the region into points of the region. And second, inverses of points on the hypersphere in n-space for n odd with respect to a parametric transformation containing the identity. This then allowed them to infer analogous theorems for function spaces, first by a method of interpolation, and second by a transition through a Hilbert space. One Harvard student who drew inspiration from both the abstract and the more computational strains of analytic research was Birkhoff's 1926 PhD student, Marshall Stone. Like Langer, Stone initially generalized some of Birkhoff's dissertation results and continued to mine this more calculational vein of research from the instructorship at Columbia that he had accepted in 1925. By 1929, though, he had not only returned to take up an instructorship at his alma mater, but his interest had also shifted to the more properly functional analytic considerations motivated by then recent mathematical discussions of the new quantum theory by Hermann Weyl, John von Neumann, and others. In a series of 3 short notes published between 1929 and 1930, Stone developed the kernel of what would become his 600-page 1932 AMS colloquium volume on linear transformations in Hilbert space and their applications to analysis. That book, described as one of the great classics of 20th century mathematics, developed the theory of possibly unbounded self-adjoint operators, that is, linear operators from a complex Hilbert space into itself that equal their adjoints. In particular, it extended from the context of bounded to unbounded operators Hilbert's spectral theorem, a result that, loosely speaking, provides conditions under which an operator or its associated matrix can be diagonalized relative to some basis. If Stone's functional analytic work followed in some sense an intellectual lineage stemming directly from Moore's general analysis, so too did the research of his older contemporary, Theophil Hildebrandt. A 1910 Chicago PhD under Moore, Hildebrandt, like Birkhoff, took his advisor's work in general analysis as a starting point from which to push the research agenda in both functional analysis and the theory of integration that he pursued over the course of a long career at the University of Michigan. In 1923, for instance, and drawing directly from then recent work of Moore and another of Moore's students, Hermann Smith, Hildebrandt gave the first general proof of the principle of uniform boundedness for what would come to be called Banach spaces. By 1926, his continuing exploration of general spaces had led him to a consideration and exposition of the Heine-Borel theorem, namely, given a set S of Euclidean n-space, S is closed and bounded if and only if S is compact. As Hildebrandt saw it, the attempts to derive this theorem in increasingly general situations have led to interesting new perspectives and characterizations of spaces. Another strand of analytic research that occupied American mathematicians in the 1920s was potential theory, or broadly speaking, the study of harmonic functions. Imported to the U.S. from Germany largely by Bochet and Kellogg, it was championed by Kellogg following his move from the University of Missouri to fill the potential theoretic void created at Harvard by Bochet's death in 1918. In the 1920s, one of the potential theoretic questions that particularly intrigued Kellogg, as well as his contemporaries like MIT's Norbert Wiener and Bochet's student Griffith Evans at Houston's Rice Institute, was the so-called Dirichlet problem of assigning arbitrary continuous boundary values to a harmonic function in the plane. By 1926, there was such a strong sense that the subject was undergoing a period of remarkable development that the AMS invited Kellogg to speak on recent progress on the problem at its January meeting. Kellogg next gave an advanced overview of the entire area in his book, Foundations of Potential Theory, that he published in 1929. So, although much more work could be singled out for mention in the analysis line, for example, the algebraic approach to function theory of Columbia's Joseph Ritt, work in approximation theory by Minnesota's Dunham Jackson and Harvard's Joseph Walsh, research on the theories of real and complex functions, as well as on special functions by Columbia's Thomas Gronwall, among others, perhaps the final major analytic research focus of American mathematicians to consider is the calculus of variations. That is, the study of conditions under which a given integral takes on a maximum or a minimum. Indeed, if Harvard was one American center of analysis in the 1920s, another was the University of Chicago, precisely in this subfield. Inaugurated there by Bolza, it was perpetuated after Bolza's departure for Germany in 1910 by Gilbert Bliss, Boltz's first and most prominent student and his successor on the Chicago faculty. As he pursued the research agenda he had begun in his 1900 doctoral dissertation, Bliss also populated the American mathematical research community with over 20 new researchers in the calculus of variations in the decade of the 1920s alone, among whom were Lawrence Graves, ultimately Bliss's colleague and successor at Chicago, and Jimmy McShane, who transplanted the field to the University of Virginia after his move there in 1935. Now, not all work on the calculus of variations in the 1920s had a Chicago connection. Roland Richardson, secretary of the AMS and indefatigable proponent of mathematics in the United States, had earned his PhD at Yale in 1906 and had worked, on Hilbert's advice, on boundary value problems with a finite number of isoparametric conditions as early as 1910. By 1928, Richardson had extended that work, although somewhat imperfectly, to consider properties enjoyed by the individual proper functions as extrema for variational problems involving an infinite number of isoparametric conditions. Also outside the immediate circle defined by Bliss and his colleagues at Chicago, George Birkhoff was active in the calculus of variations like he was in so many other areas of analysis in the 20s. Unlike Bliss, Birkhoff had come to the field from his study of dynamical systems, since, as he explained, dynamical trajectories may be regarded in many cases as geodesics along which the arc length is an extremum. Birkhoff had followed his stunning proof of Poincaré's last geometric theorem with a massive and ultimately award-winning paper in the Transactions in 1917 on dynamical systems with 2 degrees of freedom. There, among other ideas, he introduced the notion of the minimax method for establishing the existence of periodic motions of dynamical systems. One of the students at this juncture of Birkhoff's at Harvard was Marston Morse, and he followed in his advisor's calculus of variations research mode, producing a dissertation on certain types of geodesic motion of a surface of negative curvature. By 1925, Morse had pushed some of the ideas in this work further to consider the relations between the critical points of a real function of n independent variables, which drew fundamentally from Birkhoff's development of the minimax principle. The ideas that Morse presented in this paper formed the basis of what's now called Morse theory, an area in differential topology that studies differentiable functions on a manifold in order to analyze its topology. By the end of the 1920s, from the position he had taken at Harvard in 1926, Morse was hard at work developing what he called the calculus of variations in the large, an analog of Morse theory for functionals as opposed to functions. Morse's work, like that of his contemporary, Jesse Douglas, on Plateau's problem, testified to the fact that research in the calculus of variations was alive and well in 1920s America. Indeed, even more so than topology, geometry, and algebra, analysis had spread across the U.S. in the 1920s. Finally, although Americans in the 1920s were clearly engaged in research that covered a broad swath of the contemporaneous mathematical landscape, there were a number of well-established areas in which, for one reason or another, they showed relatively less, although not negligible, interest. Number theory, mathematical logic, and applied mathematics. With this, then, what picture has emerged of American mathematics in the Roaring Twenties? The 20s found Americans actively engaged in research in many of the areas of then contemporaneous mathematics: topology and geometry in their various stripes, algebra, many of the facets of analysis, at the same time that they didn't ignore others like number theory, symbolic logic, and applied mathematics. The decade marked a key transition from the emergent period in the history of research-level mathematics in the United States to a period of consolidation and growth characterized by the production of future researchers as well as by research productivity in areas both traditional and cutting edge at colleges and universities from coast to coast. This was the new lay of the American mathematical research landscape that allowed for the successful transplantation in the 1930s of mathematicians fleeing the ever-worsening political situation in much of Europe. These mathematicians did not, as conventional wisdom would have it, transform a mathematical backwater into the international leader in the field. They joined a rich and vibrant mathematical community that, like American society as a whole, had developed and prospered in the Roaring Twenties. Thank you.